welcome again, everybody. I think we can start. My name is De Santi Stefani. I'm the coordinator of the EC Communities project. It's a project funded by the Horizon Europe and a project that aims to support and valorize the EC beneficiaries that are implementing EC projects. We are working closely with the European Innovation Council, and the today event is organized with the European Innovation Council, in particular with the EC program manager Hedy Kerry, and Isabel Obieta and Samira Nick. EC Communities is a project that is implemented by APRE, the Italian Agency for the Promotion of European Research, together with its partner, ICONS from Italy, ABN from Belgium, that is the European Business Innovation Network, EURA from Portugal, and now we are working for the implementation of this series of webinars dedicated to artificial intelligence with the EC program managers. I just want to spend 2 words for the activities beyond this series of events that are the pitching sessions that are taking place in September. And I share briefly my screen to give you just some information to this pitching session, because it's a great opportunity to meet EC projects. So please let me know if you are able to see my screen.
Yes, Stefania. Not in presentation mode, but yes.
Okay, perfect. So I put it in full screen mode. And I see that, I suppose that in a while you will see it. Please, Jessica, let me know when you see the screen.
No, not yet. We still see it in normal mode, not presentation mode. Now, yes.
Okay, great. So as I was telling to you, we are organizing these pitching sessions from the 22nd to the 24th of September. The first one is dedicated to clean tech projects, the second to industry projects, and the third one to health projects. So in this phase, we are recruiting the projects that want to pitch and showcase their results. And in the meanwhile, it's possible for the stakeholders, so it means to research organization, universities, corporates, and investors too, to participate to this pitching session and register to them and show their interest. It's possible through the project website that is deepsync.eu. Then I will let you the link in the chat, but also from the registration form. You see here there is a link that you can click on, and we send you this presentation after the today webinar to see all the projects belonging to our communities. So you see the projects, the description, and through the registration form you can express your interest to meet the project and listen to their pitch during these 3 days. If you scan the QR code, you can see, you can watch also the events webpage and have more information on that, and see which are the projects that have already giving the availability to pitch, so you can monitor constantly the situation. So if you want to meet the EC projects, you want to listen to their pitch and listen to their results, you can register to these 3 days event and express your interest for specific projects too. So I will let you the information in the chat, and then with a follow-up email, so you can stay informed about these initiatives. I give now the floor to the EC Program Manager Hedy Kerry for a brief welcome words and the introduction to the today webinar. Thank you, Hedy.
Thank you, Stefania. Hello, everyone. Thank you to joining this webinar. Just to give you a quick idea about this series of webinar that we are organizing, we call it Behind the Hype. AI is not anymore a hype. It's happening. Change is happening. So the objective is to discuss with the community, with people making AI and also people from the academia, from the business. So the whole ecosystem making innovation and making innovative solutions in Europe to raise their voice, to present their innovation, but also to shape the future together. So the idea is to build with you, with the speakers, with the attendees, the roadmap for the future innovation in responsible AI that Europe is committed to ensure. So happy today that we are talking about a very hot topic about the AI infrastructure in that hot day. I don't know, this is the case in Brussels, but I think in most of European countries, it's a very hot day. So happy that I said we will go through different topics related to the AI infrastructure. And now is a matter of sovereignty. AI infrastructure is a matter of sovereignty, is a matter of leadership in order to run the further innovation and upcoming innovation in AI. Happy also that we have distinguished speakers today to learn from them, to hear about AI infrastructure, but also to hear from AIC awardees. So we are happy that we have two startups today. One of them is SpinCloud, just selected and announced 2 days ago that they are selected for our accelerator program, and then also Multiverse Computing, which were selected for our STEP program. So happy to have them on the board today to talk about that. But we'll start with more introductory presentation on the background on what is happening in this area with Professor Shahram Dassar, who is full professor of computer science at TU Wien. He's heading the research division of distributive systems Austria, and also he's part of ICREA research at UPF Barcelona. Also, he was the co-founder and chief scientist of Caramba Lab software in Vienna. Also, he's the co-founder and the chief scientist of Kuvali AI, an AI infrastructure company based in Barcelona. So happy to have you on board today, and I invite you to share your screen and give us your insights. Thank you, Shahram.
Thank you very much, Eddie, for the kind introduction. Can you see my slides?
Yes, perfectly.
Yes.
Okay. Wonderful, wonderful. Thank you very much. Yeah, so I'm going to speak on my perspective on AI infrastructure. So since the information I got initially was that the audience is very diverse and I should give a broad overview, I try my best to do that. So AI infrastructure in the computing continuum is the topic. I will speak first in general about what do I mean with the computing continuum and the AI infrastructure in particular. And then I will give you some examples of my company, Kuvali, what we do actually in different projects. So the computing continuum is actually a fabric of computing devices. It ranges from, let's say, IoT on the left-hand side, edge, fog, cloud computing, and encompassing, in principle, also high-performance computing and quantum computing in the future. And the idea is basically, instead of looking at just everything on the cloud, to actually have a distributed perspective on the whole infrastructure. And this is justified by multiple applications today in healthcare, autonomous vehicles, smart cities, etc. But the problem is that today we just have a centralized and a very limited visibility of the overall system. And the idea of the computing continuum is to extend that perspective and look at it from the global view, spanning from the sensors, edge, fog, cloud, and so on. And there are a couple of problems related to that. One is that the overall computing continuum is multi-proprietary. This means that we have shared infrastructure ownership, and every stakeholder has his own global interest, have local requirements of the infrastructure based on where the service provider is actually located. And we need many different tools in order to be able to actually manage those things. The second fundamental problem is that it's geographically distributed. This means that we currently do not have any form of decentralized governance that considers the local characteristics of the services and the host that typically the service and the hardware is provided for. And these are large-scale challenges that we have nowadays. That is in principle true for the whole computing continuum and not special for AI infrastructure. But of course, if you bring in AI as well, it has its certain flavor in addition, because AI is, of course, not just LLMs, which are very centralized nowadays, but actually there is much, much more. I will talk about that a little bit later. So we see that these types of computing continuum are actually very complex. So when we speak of complexity, I like to bring the example of the human body. The human body is actually a nice example of a complex system. We have the skeletal system, we have the nervous system, the cardiovascular system, and they constitute the infrastructure of our bodies, right? But we have more. We have the lymphatic system, the endocrine system, which are responsible for the regulation. And what is interesting is that the nervous system is actually controlled by the brain. The brain is a big computational engine. This is my argument here. When we look at the brain, it is consisting of 86 billion neurons, and it's the most powerful computer that we possess in our bodies. And this has been the metaphor for computing and computer science in general. We are all used to that, right? So computers as the brain. However, I would like to make this analogy and take it a step further. It's not only about the brain, because if you look at the human body, there is more. There is also the heart. The heart has 40,000 neurons. So this is the second computational center that we have in our bodies. And the third computational center is the gut. It has around 100 million neurons as well. So in effect, we have three computational centers in the body, which constantly message each other and exchange biochemistry. And this is needed in order to keep us in a homeostasis, in equilibrium, so that we are able to function properly. So for example, our heartbeat is not controlled by the brain. It is controlled by the autonomic nervous system, which is very good, because otherwise we might forget to breathe and simply die. And then evolution would have a sudden end, which is not very good, right? So there is, of course, more. We have also a regulation system, a security system, in a sense, that is part of the immune system against foreign invaders, etc. So what I'm trying to say here is that we have three computational centers in the body. And I want to make this analogy to the edge, to the fog, and to the cloud. It's kind of similar. This is why I bring this analogy, so that people can remember. It actually makes sense to look at the infrastructure from this holistic perspective, right? So let's look at the infrastructure aspect. And this is the thing that I focus on here. How do we actually deal with the infrastructure? And we thought a lot about this in the last 10, 12 years. And we came up with a construct which we call deep SLOs, which I will speak a little bit about here. But there is more about learning, of course, because every complex system requires learning and also security issues, but I don't talk about them here. So when we look at the body is actually resilient or anti-fragile, if you like, and always maintains a homeostasis. It maintains a basis, a balance, an equilibrium. And this is reflected in the temperature, for example, or in the blood pressure. However, we are not able to say and access the details of what is going on. So for example, when I ask you, Hedy, how are you feeling? You might be able to say, okay, I feel hot. My body is trying to compensate for that by sweating, but you don't have access to the deep values of your liver or your kidney, right? So this is an issue that we constantly face with the body. So that's why we do blood measurements. And similarly to the complex computer system in the compute continuum, we need to actually be able to have a deeper dive into what is actually going on in this computing continuum, so that we are able to sense the overall state. So how are we able to do that? And this is something that we currently, with the current paradigm of developing software, and that includes AI, we are not really able to do in a very well way. So let's look into this. And the fundamental property of resilience in a system is the foundational idea of elasticity. Elasticity is a requirement for resilience. This means that from physics, when we put force on a material, it stretches. If we take away that force, it goes back to its initial form, right? And this is a property of a system that we would like to have. We would like to have that ideally in the infrastructure itself. This is something that we are, let's say, working in the last 10 years, but with a very special semantics. So you might say elasticity, isn't that the same like scalability? And my argument is that it's actually more, or it should be more. So scalability deals with the resources that we use. So we have resource elasticity. But my argument is that we have two more dimensions in the elasticity space. One is quality elasticity, meaning the quality of the data input and output, and cost elasticity. And we as engineers, we have to typically manage all three criteria at the same time when we build systems on top of this computing continuum. So in other words, taking care of the quality and the cost in concert with the resources is key for us. We cannot just do one of these, right? So we have to constantly trade these different criteria with each other, so that ideally we reach an equilibrium, a high level state, which is balancing the overall equilibrium of the system, so that not like in this picture with the ship that it tilts to one side, but is actually able to maintain its equilibrium. So how do we do that? We look into the foundational concept of the service level objectives. Most people are familiar with service level objectives. These are essentially system controls or requirements, if you like, and they represent thresholds in a three-dimensional Cartesian space. And they delimit the space inside a hexahedron. So this means in this three-dimensional space, we can have these constraints of the infrastructure represented here visually by points. And the valid infrastructure is then represented here as a blanket, which is a stretch blanket in this case of possible configurations overall. So this is a mathematical representation visualized here, just to make the illustration of how this actually looks like. So translated into the world of systems, this means that every infrastructure which is inside this blanket is in equilibrium, all right? So how do we do that? So we look at the mathematical construct or concept of Judea Pearl, the ACM Turing Award winner in computer science, who defines a Markov blanket of a random variable as a node n here in this little example, with the parents p, the children c, and the co-parents of the children s. So in other words, when we look at the directed acyclic graph of a node, we basically filter out all the other criteria which are not relevant for the time being. And we just focus and zoom in into one node, how things, and put our attention to that one. This is the core of active inference. So the Markov blanket then uses the sensory information that we have in the IoT sensors and whatnot, and basically links together all the constructs that we are using in the system and puts together a system perspective, a filter perspective of the infrastructure that we are dealing with. Now, active inference is quite different to the traditional machine learning approach. Let me explain a little bit more what I mean. In the machine learning approach, in fact, it should be called maybe more appropriately machine teaching. We take data and feed it into typically a large-scale cloud system where we look at the patterns and then we infer what is the actual object that we are looking at, right? Active inference is a concept that comes from neuroscience, and it has a different approach. It says that as a human, we have a different approach to learning. This is represented very clearly when we observe children. We can see that the child sees one cat, for example, and knows then what is a cat, right? It's very different to traditional machine learning approaches. And how does it work? And in active inference, the most cited author is Professor Carl Friston. And since many years, more than a decade, he's speaking about the active inference framework in neuroscience. And what neuroscience does, and this kind of bleeds over to our AI research, is that the objective of active inference is to minimize the free energy. Free energy, in this case, has nothing to do with physics. In this case, it's a measure of uncertainty, and it is about the amount to maintain homeostasis, what I was talking about before, and the prediction of any changes in the environment of the infrastructure. So in other words, the free energy principle then tries to minimize the difference between what I predict and what I actually get as a sensory input from the world of data that I'm creating. And then I use Bayesian inference to use probabilistic models to update the beliefs that I have about the state of the world based on that new data. And only then I update my belief, not constantly, right? And we see that clearly with human learning, that we create a generative model that we built about the world, about large things, about small things. We create a model and we minimize the energy we need in order to create that model. And then we always also minimize the energy to actually maintain that model. Only when something major happens, we are forced to change our belief about the model that we have created. And then under a lot of protests, so to say, we change our view on certain things, right? This is the perspective on generative models. And then we use three mechanisms in order to achieve this. We have the perception, updating our beliefs based on our sensory inputs. We have action. This involves selecting certain actions that minimize our expected free energy by reducing the prediction errors. And finally, learning. We adjust the parameters of our generative models to improve the future predictions and actions. And the active inference framework then is the whole combination of these mechanisms that I was just speaking about through Bayesian inference and generative models and prediction of what will actually happen. So now what we do in our work, besides other things, is to utilize active inference as a framework to create an infrastructure of distributed active inference agents that allows us to learn similar to how the human is learning, with the goal to actually distribute and decentralize the whole learning and, so to speak, intelligence of the system across the complete computing continuum. So in other words, we have edge, we have fog, we have cloud, and in the future, other parts like HPC or quantum possibly, where we distribute the intelligence so that the overall infrastructure becomes intelligent and not the applications themselves. So we try to push the intelligence into the infrastructure. This is the, let's say, the large scale goal of what we are doing in my research. Now, let's link finally a little bit to what we do at Co-Valley. So Co-Valley is actually an AI infrastructure fabric, which allows to integrate and manage all these different data providers that I'm talking about, the edge, the fog, and the cloud, and allows us to model deployment and management also for the end users, and that across this whole computing continuum. So we can go either completely on the cloud or completely local on-premise or something in between, which I find, or we find, very, very relevant and important in the landscape today, because many companies are not comfortable with uploading all the data to some cloud. They would prefer to have large portions, if not all data, maybe on-premise. And this is very important to comply to. We also have a fabric for models. So we basically have the AI model market, where we maintain an infrastructure of all open source models for different vertical industries. In this case, one of the customers is rail, where we maintain these different models that are learned across the different rail infrastructures. We are able to manage then the computing clusters, which are distributed, can be partially on the edge of the network, can be partially on the cloud, or anything in between. And we allow to manage them very easily and deploy these edge learning models also very easily from one interface only. So you can have inferences on your edge devices or on the cloud or anything in between that you might choose, the GPU, CPU, whatever. So the platform basically looks then into different types of processing, can be tables, can be images, can be videos. We have automated model training, API generation and management, and allow to integrate all of these together in an easy-to-use workflow as well. And of course, security is an important part where we are GDPR compliant and support end-to-end encryption as well. Some examples that we do are, as I said, transportation, can be mobility scenarios in a smart city where we predict traffic, flow prediction, traffic monitoring, or rail systems that we do a large project, or in manufacturing where we do visual inspection or predictive maintenance, where we analyze the different parts of a technical component, for example, like a train, and this is automated in a very speedy way to find little problems in technical pieces of equipment, because this is the strength of AI actually versus the human who has to look into where is this little crack in this piece of technology, like a part of a rail or something like this. So this is very practical. This is what our users actually utilize. Important for me is that the AI infrastructure has to be seen as a composite, as I call the computing continuum, where we have an understanding and a perspective of integrating the edge, the fog, and the cloud. And we have to be able to find constructs from the scientific part so that we are able to model the systems that are operating on these types of infrastructures in a coherent way, where we as humans, when we build these systems, look at the overall infrastructure and leave the intelligence to the infrastructure. In other words, I don't want to control everything at all the time explicitly, where to be computed, where to be run at. I would like to have the infrastructure be intelligent and say, okay, if I have this edge infrastructure now available, let's make use of that edge infrastructure and allow a better utilization of these parts of the system, and make that in a good predictive way based on real data. And this is what we do. And with that, I thank you very much for your attention.
Thank you very much, Sharon, for this presentation. I don't know if there is any question from the audience, so you can use the chat to ask questions. We'll have more time later in the panel. But I have one question while you are talking about this amazing computing continuum. It came to my mind the challenges at the gap currently when we would like to design this continuum from, let's say, from the edge to the quantum. So if you can give us some insights quickly on that.
Yes, so I think from the edge to the fog to the cloud, we are actually able to do it. With the quantum, not quite conceptually, because there are many different challenges. The quantum side is very challenging because, of course, it is very hard to read the data out of a quantum system, right? Without destroying it, etc. So getting the data out of a quantum system is extremely hard, if not impossible, by definition. So that is challenging. So I'm not sure if in the next 10, 20 years, we will be able to integrate the quantum system into this computing continuum. Where I'm more optimistic is high performance computing. This should be possible because the boundary between cloud computing and high performance computing is much thinner than compared to quantum computing.
Perfect. So I think we'll have more discussion later during the panel about the topic. So now I will invite Hector Gonzalez, who is the CEO and co-founder of Spin Cloud Systems. Spin Cloud is a deep tech company providing brain-inspired microchips and systems for the new generation of sparse AI models. And as I said, they have like it's a success story of the European funding coming from the Brains project to the transition at AIC, and then now they awarded the accelerator program. So Hector, welcome, and the floor is yours.
Thank you so much, Heidi, for a very kind introduction, and also for the invitation. It's a pleasure for me to be here presenting to you. And as you mentioned, I mean, we're very happy that we just received the news from the EIC Accelerator. So to tell you a little bit about our project. So our project, the inception of our project was the Human Brain Project, which is this European flagship human brain project where Europe invested resources to understand the brain from different disciplines and also design systems that behave like the brain. And our system or our technology was a child of the Human Brain Project. We also were lucky enough to be part of the EIC Transition Project, which also enabled us to design compilers for our infrastructure and also enable us to expand sales of our infrastructure worldwide. And now we are very happy to basically be awarded to the EIC Accelerator that will significantly boost our traction, the traction that we have up to now. So yeah, it's a pleasure for me. So I'm Hector. My background is in chip design. So I am the CEO of the company, but I come more from the deep tech side domain, and I will be talking a little bit about brain-inspired computing at large scale. So the previous presentation was already very interesting, and it also shares different ideas that we also envision as to how to integrate systems within regular infrastructure, especially because the brain, it's not an isolated or central processing unit that has no interface with the outside. In fact, there are different processing components at different hierarchies within the human body that basically are all around the nervous system. And even within the brain, there are also different hierarchies that are also quite synergetic and complementary to the previous approach. So I'm happy to actually take it over from there. So the challenge we're behind, or let's say the two challenges that artificial intelligence has today is essentially the huge energy consumption of artificial intelligence, and also that these AI models are still not very robust. So these models of today, even up to the new reasoning models, they still hallucinate significantly and also make up facts, which might be okay for, let's say, chatbot-based application, but not for mission-critical applications like in the defense domain or other applications where you might want to incorporate models that have high robustness scores. So these two challenges are challenges that we have looked from a perspective of flexibility into the technology. And I'll be talking slightly about the two of them, but more from the energy point of view. So essentially, we are at the moment at the boundary of a huge energetic crisis. So artificial intelligence today is consuming so much that AI data centers are really consuming as much as entire countries. And experts are warning us that by 2040, like the globally produced energy that we will generate will be required only to power AI data centers. So this is clearly, so if you think about it, this means that pretty much all the energy that we will produce is just to power artificial intelligence. So essentially, this is the reason why different industries and different big corporations are also searching for alternative ways of energy, some awakening nuclear power plants, just to be able to catch up with the power requirements that are required from the grid to be able to provide this power for AI data centers. I mean, this is one alternative. There's also other alternatives, that is to design more energy efficient infrastructure and also more energy efficient algorithms. Talking about algorithms, I mean, the huge spike in energy consumption is basically caused due to scaling of models. So artificial intelligence has made tremendous breakthroughs today. I think we all have used them in one way or another one. But the reason, or let's say the reason why we are able to experience those breakthroughs is because models have been scaled significantly. So, and this growth of models is something that is not likely to change too much. So there are alternatives to scale in a more strategic way, as I'll mention in a moment, but still the trend is that models are growing and it will continue to grow. When we look at, let's say, the computational blocks of the building blocks of state-of-the-art AI models, I mean, we have to look at kind of the fundamental block of the use today, which is transformer-like architectures. So essentially, the most computationally expensive block of transformers is what's known as the feed-forward block. Basically, the feed-forward block is like a large, dense MLP in which you have to compute several paths in parallel. This is less essentially from an algorithmic standpoint. This block is essentially the most computationally expensive block. So people have discovered, like top leading groups, like from DeepSeek, Meta, Google DeepMind, Microsoft, have actually discovered that when you execute this type of networks, there are certain paths within this network that contribute the most to the outputs. So these paths are actually isolated into sub-networks, and then only these sub-networks get to be triggered during the execution of these models. This is what's known today as mixture of experts, and it's essentially the state-of-the-art of AI models today. Like models, like the new models that you experience today are more and more using these type of MOE type of architectures. And these MOE type of architectures are also being pushed to the very extreme. That is that you have many, many experts with a small computational footprint. So Google DeepMind has an algorithm that's called mixture of a million of experts, where essentially you have a very large number of experts with a very small computational footprint. And Meta has also something that's called memory plus blocks that also goes in this direction. So essentially, before we talk about the details of those extremely sparse models, I mean, the trend is that models used to be just a pure parameter scaling approach, where basically you were just scaling parameters, just increasing parameter count, until it was really saturating the growth. So then people started to look for strategic ways to actually scale. And these strategic ways is scaling through this sub-networks of this mixture of expert type of approach. So we are seeing more and more these increase in the utilization of MOE type of models. So like when you look at state of the art, more and more is of the new models are kind of embedding these type of efficient computation blocks. And the consequence of this is that we are also getting better and better performances in these models. The trend that we see in very large number of experts and very sparse with very fine granular MOEs is that people have shown, essentially experts have shown that when you have a high number of expert count, your performance is actually improves, especially for large number of parameters. So higher number of experts leads you to a better performance and also leads you to have a very good computational footprint. The problem is that in today's architectures, essentially scaling this sparse MOE type of architectures faces a critical constraint. So for example, when you start to increase the number of experts in regular GPUs, the higher number of experts no longer leads you to the best performance, because now the routing costs of having high unused compute on these regular GPU-based or GPU derivative architectures does not lead you to further performance improvements. That's why most of the MOEs and the sparse MOEs rather stay with a limited number of experts. This is what Google DeepMind has shown, that basically the desire would be to have a very large number of sparse architectures with a very small computational footprint, where you still implement the full network, but you need Fabric to just compute like this small footprint that relates to the expert. So this is something that architectures today are not very good at. So when we look at the GPUs of like GPU architectures, they are very good at these dense type of models that exist today. So dense, when you look at the horizontal axis of this scale, left is very dense models and right is very sparse models. So essentially GPUs are very good at this dense execution of models. And GPU derivatives, like, for example, architectures like Cerebras, Grok, Samba Nova, they are actually better than GPUs at computing these dense models. So they have improved a lot of the communication bottlenecks and a lot of compute problems that GPUs have. For example, Cerebras uses a big wafer where you have very good compute densities, you have very good communication fabrics to improve the execution of dense models. But then when you go to the right side to these very fine granular sparse models, what you have in these two types of architectures is that you have a lot of unused compute, because you have this very small footprint of experts that is essentially wasting compute. So architectures like in-memory compute or near-memory compute paradigm have fundamentally better infrastructure to support these fine granular experts, but especially these type of brain-inspired topologies where basically you get to trigger individual elements in this event-based type of computation. You have a better footprint and a better compute utilization to push forward these extremely sparse models, as I'll mention in a moment. And this is where the motivation comes to look at the human brain, because essentially the human brain is, as it was mentioned in the previous presentation, I mean, it's extremely good at sparse computation. It really excels at sparse computation. When you think about it, we have a lot of computational neurons, but they are never engaged in this dense approach. They are rather engaged in this strategic approach where only certain parts of the brain are engaged in a particular instance of time. So the human brain only consumes the amount of energy of a light bulb and can do things that basically artificial intelligence today still can only dream of, and also have very extremely high robustness. So these are the things that we have considered for important and key for this next generation of systems, especially to tackle those extremely sparse workloads. So when we look at brain-inspired hardware, like basically there is a huge spectrum of what it really means to be brain-inspired. I mean, biological brains are extremely good at what they do, but there's still a lot of mystery as how the human brain operates. So designing brain-inspired hardware really narrows down into what does it make sense to copy from biological brains to enable you to design extremely efficient systems, and what things not to copy from the brain, because this still remains a mystery, or just because the substrates of the brain offer significant advantages for certain type of computational primitives. So when you look at the spectrum of brain-inspired hardware or neuromorphic hardware, there are different levels of abstraction. So at the very low level, you have people that are designing, for example, memristor-based devices, designing devices at a very low level and optimizing computational primitives from the brain at very low level. When you go slightly up, you have people that are leveraging, for example, analog compute to design these brain-inspired systems, like, for example, the Heidelberg team with the BrainScale system. So if you go slightly up, you find all the companies that are leveraging analog mixed signal, like, for example, the Inatera systems. If you go slightly up, you find the digital systems, like, for example, the Loihi systems or the Simpson systems, that they are encoding computational neural dynamics into RTL. If you go slightly up, you have systems that are using off-the-shelf FPGA, that they do not offer you any energy advantages, but they let you reconfigure different prototype, different architectures. And then you go slightly up into architectures like ours that essentially have the hardware backbone to implement different type of brain-inspired principles while giving you full flexibility. Why full flexibility is important? Because there's still not a fundamental reason or justification to bring, for example, spike-based computation into today's models. And this is not something we do. I often distinguish ourselves from actually a brain-inspired infrastructure that's not married to implement spike-based computation. For example, we can implement regular deep neural network operators, but just leveraging these computational principles from the brain to implement sparsity in regular DNA computation. And this is where our architecture strategically sits, so that you get to leverage these brain-inspired principles while at the same time deploy models that are used in today's mainstream AI models. And this is exactly the sources of inspiration that we find interesting from the brain, that do not constrain us or commit us to just mimic the brain for the sake of mimicking the brain. So we're interested in connectivity, scalability, in distributed processing, in highly scalable processing, in globally asynchronous characteristics. Also, the fact that the brain consumes energy in a very strategic approach, in an energy proportional approach. And this is exactly what we have encoded into our system. So essentially, our top-level supercomputers are encoded in these toroidal type of mesh networks. So every individual processing element is one of our microchips, and then it can let you implement sparse processing, sparse and distributed processing. It can let you encode energy proportional behavior, and it also lets you deploy extremely large models that are partitioned in a very strategic way to leverage this distributed low power characteristics. So the fundamental building block of our current product is the Spinnaker 2 chip, that is this hybrid microchip that lets you implement these different type of AI operators. So we have a distributed low power mesh of low power processing elements that are all interconnected in a network on chip like this. So we have also strategic patterns to interconnect chips to chips. We also have some custom LVDS links that let you interconnect chips to chips and also extend hierarchies like these toroidal type of hierarchies. And we also have patterns for fine granular control of these cores. So note that this is not about spiking. It's more about how you can engage processing elements in an event-based approach. So in an on-demand basis. So for example, if you have a sensor stream that basically is stream into these 4 cores, you can actually sectorize the sensor stream into 4 quadrants and then shut off the other cores that are unused when the sensor stream just leaves the relevant quadrant. So this allows us to have very fine granular control on the actual footprint that it is consumed, and it lets you implement these extremely sparse networks where you only need to trigger specific portions of the infrastructure, which also leads to huge energy savings when it comes to computational footprint. We take this concept of this microchips, we group them into this boards of 48 chips, and then they get strategically interconnected at large scale to encode this toroidal network, and they get strategically folded and they go into these type of rack systems. And these are the systems that we commercialize. So we commercialize arbitrary sizes of these supercomputers. Essentially, we have built the world's largest brain-like supercomputer in Germany. So it is the top leading supercomputer that basically reaches scales that are not possible to reach by other supercomputers. It has been featured in Nature publications, co-authored by different members from the HPC domain and also brain-inspired supercomputer domain, including members from Intel, Meta, Google, that highlight the characteristics and the scale of our supercomputers. The product that we have then commercially available is, as I mentioned, the supercomputer. So we have sold it worldwide to different leading institutions in the US and also in Europe. So our system is a strategic platform from the US Department of Energy. So when you go to the US Department of Energy, it's listed as one of the strategic platforms to pursue energy efficient AI. And then we're also working in another microchip and another supercomputer that commits more to these dynamic sparse foundational models that we will also introduce soon into the market. The software, I mean, you might wonder, this supercomputer, these distributed cores and so on must be difficult to program. Essentially, when you think about the supercomputer, there are 5 million low-level C programs that are running in parallel. So we have a software infrastructure that was actually funded by the EIC transition, which you have certain strategic pillars so that you can use the infrastructure without the complexity of going into programming the low-level processing elements. So as I mentioned, the infrastructure sits strategically into different types of AI fields so that it leverages different characteristics of the field. And I can take you through a few of the applications that are basically deployed in the infrastructure, and that also show some of the characteristics of the system, just to close the presentation. So one is this neurosymbolic models. So neurosymbolic models that leverage rule-based type of engines combined with deep neural network fabrics within the same supercomputer. So these neurosymbolic models are actually more robust than typical pure GPT-based models, and they are very difficult to scale up in regular infrastructure because typically these deep learning accelerators only focus on the numeric part of the deep neural network. So it's a model. This one is in particular is called NARS. It's non-axiomatic reasoning system that combines a deep neural network together with a reasoning. This is particularly relevant for the defense domain because it can deploy very robust models. Efficient language models that leverage these event-based and dynamic sparse characteristics. Also, we have a pipeline that lets you sparsify existing models so that you can sparsify those MLP blocks into these peer-like blocks so that you get to leverage these dynamic sparse characteristics of the hardware. We have also optimization problems that have shown to outperform the existing state-of-the-art hardware. In this particular reference point is more CPUs. CPUs are the state-of-the-art because GPUs are not very good at this problem. So CPUs are rather the state-of-the-art solutions. And basically, we can achieve the same costs of the same solutions at a fraction of the energy. So this is also work that has been published in Nature. Also extremely complex mathematical processes that are very relevant for solutions to national security problems, where you get to leverage extremely sparse and highly parallel characteristics of the infrastructure. Drug discovery applications where you deploy small MLP models that talk to each other within the highly parallel fabric. So this also leads to converge extremely fast at a fraction of the energy. And just to close, because I think I'm slightly over time, key takeaways thing is basically the infrastructure is very good at this high degree of parallelism. So it's very good at leveraging these dynamic sparse workloads, particularly relevant to how these mainstream AI models are going to. So then it's extremely useful to deploy workloads that are going to be very repetitive and can be crafted and optimized for energy efficient deployment. And in general, like one of our theses is that basically biology has spent like millions of years of evolutions optimizing systems like the brain. So it really makes sense to look at brain inspiration to define and design systems. So this is my last slide, and I'm happy to take questions.
Thank you. Thank you very much, Hector. I don't know if there is questions, please go through the chat because we are a bit late in order to have time for the panel later. But one of the questions that maybe you can think about and just give an answer in the chat is about the commercialization, because now is the race regarding the AI infrastructure with HPC and so on. So how do you see the perspective in the next decade in terms of brain-inspired computing, and what is your position about that? Okay.
Yeah, should I answer it straight away, right?
Yeah, please go through the chat to answer that, and because I have to give the floor to Victor from Multiverse Computing. So I'm happy to invite Victor Gaspar, who's the Chief Sales Officer of Multiverse Computing. Multiverse is one also of the AIC champions, went through our accelerator program and then now with the STEP program. So Victor is also member of Euro Quick and the Quantum Technologies Quantum Technologies Working Group at Amitic. He's also actively contributing to the advancement of quantum technologies in Europe. So happy to give you the floor and hear your insight and what you are doing in multiverse computing.
Yep, thank you very much, Hedy, for the introduction. I think we're very much in line with the two previous speakers, with Professor Sharam and Hector. So let me start by introducing the company. Okay, who is Multiverse Computing? First of all, we started in 2019. We are a startup company, although we are right now 170 people. We have sustained revenues of 20 million euros last year with the aim of duplicating the revenue this year. And we recently closed a Series B of $254 million. As a company that works on deep tech, we do try to publish as much as possible to show the technical soundness of our approaches, but also as a company that wants to protect its know-how, we have submitted many patents in the last years. Okay. When we started as a company, and you mentioned well that we work on quantum computing and quantum AI recently, quantum computers has been previously mentioned by Professor Sharam are the early stage computers. So quantum computers right now cannot solve any meaningful or industrial problem. And this is even if it's a super interesting technology and it is super interesting technology, you cannot solve meaningful problems today. Okay, everything that you can do on quantum computers is research-oriented projects. And for us as a company that wants to deliver value today to customers, this presents a challenge. Okay, so since the beginning, and thanks that our one of our founders, Professor Romano Rus, is an expert in type of techniques called tensor networks that are quantum inspired. We have always used in the company these two approaches. One that can deliver value today, it's quantum inspired methods that I will explain right away, and also pure quantum approaches. So basically techniques, algorithms that run on pure quantum computers. Okay, what is the interesting part of using quantum inspired techniques like tensor networks is that those algorithms, those techniques run on classical CPUs and GPUs. So you don't need to wait for 10 years for a quantum computer to be ready. You can deliver value today. You can run on those algorithms, the same that Hector was explaining, brain-inspired architectures. This is quantum-inspired architectures, but they run on classical CPUs and GPUs, so you can deliver value today. Okay. Particularly, we use type of techniques that are called tensor networks. Those techniques are a mathematical framework that was invented many, many years ago, like 30 years ago. So it's a well-studied field. It was invented. This type of techniques were invented in condensed matter physics to reduce the dimensionality problem of simulating or representing large entangled quantum systems. Okay, these type of systems are highly dimensional and are really difficult to simulate using classical computers. Even nowadays, the largest HPC infrastructure cannot simulate small molecules. So these techniques were invented like 30 years ago to try to reduce that problem, the size of that problem, and tackle the different components of that problem. Okay. What we have seen in the last years, probably in the last 10 years, is that sorry, there's a notification here. So in the last 10 years, what we have seen in these last 10 years is that we can use the same techniques to reduce the dimensionality problem of neural networks. So basically, we can take a neural network, analyze that neural network using tensor networks. Okay, so we create a tensorized neural network that we call it. Okay, and focus on the relevant parts of the neural network. So basically, we analyze the correlation space of the neural network, and we keep the focus, let's say, on the important part of the neural network, and we remove the rest of the neural network. What does it bring? What brings this reduction in the size of the number of neurons? Basically, it means less parameters inside the neural network, so less memory. It means that if you want to retrain that neural network, it's going to be faster because it contains less parameters to train. The inference is faster because you have a smaller neural network, and you will require less hardware. Okay, so basically you will save money. As I said, we were using this type of techniques since 2019, 2020. And for different types of neural networks. So for dense neural networks, convolutional neural networks, but it has been in the last years that this has taken a focus, and I will explain right now why. It is also interesting, these techniques and these tensor networks techniques, because since they are inspired on how quantum mechanics work, we can take a path from these tensor networks to a quantum gate-based circuit. So any tensor network representation can be transformed in a quantum gate-based circuit. So you can always run this circuit on a quantum computer. So once these quantum computers are ready in the future, we will be able to transform and move any tensor network representation into a quantum gate-based circuit and run it in a quantum computer. But that's, of course, is much more experimental. Okay, that will require a lot of effort. Nevertheless, if you are more interested on this type of approaches, we have, for example, simulated the latest IVM experiment, this quantum utility experiment using tensor networks efficiently on tensor networks and simulating the largest quantum system, quantum IVM quantum system using tensor networks on classical CPUs. Okay, so that's an interesting approach that probably in the next years will take an advantage. We will take an advantage of that. Why is interesting reducing the size of neural networks? This has been mentioned before by Hector. We have seen since 2012 that is what many people in the field call the AlexNet moment, is that in 2012, 2013, there was this competition where a group of scientists from Stanford started using GPUs to train neural networks that are much more efficient. Since 2013, there has been this exponential increase in the number of parameters of neural networks, of classical neural networks. Okay, so we can see clearly this exponential growth of the size of the neural networks. This exponential increase in size has not brought to the table an exponential increase in accuracy. Okay, we have neural networks that are linearly better to previous generation. Nevertheless, they are exponentially bigger than previous generations. Okay, so this what it tells us is that there are inefficiencies embedded in those neural networks. So what it's telling us is that probably the field still require more research, right? And this is the problem precisely that we are tackling, reducing the amount of, let's say, redundancy inside neural networks, the amount of noise inside neural networks, and making them more efficient. Okay. By using tensor networks, basically we can reduce the amount of parameters, so we can run them probably on the edge, on small devices. We can consume less energy. We can make faster training and inference, consuming less memory and less cost. Okay, let me show you some real metrics that we have obtained with different types of neural networks. In this case, are large language models that, because of their size, these benefits are more clear. So, for example, we can take a Llama 3.3 70B model, it's a 70 billion parameter model, and reduce it 80% in memory. So 60% in the number of parameters, 80% in memory, using tensor networks, and which benefit this brings to different KPIs. For example, reducing 80% in memory, a Llama 3.3 70B model, and comparing it against the original model or against classical techniques like quantization, we can see that we can basically double, so reducing half the latency of this model, the time to first token, the time the model takes to produce the first, let's say, word. Okay, we can reduce in half that time. Okay, also taking into account, for example, the Llama 3.3 70B model, we can see compare against the original model and the quantized version that we can double the throughput. Okay, so we can produce 2 times more tokens per second than the original model. Okay. And that's interesting if you own the data center, and we're talking about AI infrastructure, because this is important because without changing your data center, we can double the number of users that this data center can serve. Okay. In some other approaches, you need to change the underlying hardware to get some of the benefits. Notice here that we are not changing anything of the hardware. We are basically taking the original model, applying our techniques, producing a compressed model, a reduced size model, and we get some benefits out of that, like, for example, latency, as I was mentioning, or doubling the throughput. Okay, if we take energy into account, for example, the energy consumption, we have measured Llama 3.1 energy consumption, and we can see that we can reduce at best like 50% the energy that you need to run these models. So it's a range between 30 and 50% reduction in energy compared against the original model. Okay. Also in RAM, we can see the amount of RAM memory that you need to run the original model versus the tensorized model. Okay. All on that, with a maximum drop in accuracy of up to 3%, on average up to 3%, 3-4% drop in accuracy, depending, of course, on the model. So what we can see is that models, LLMs particularly, are highly over-parameterized. So it contains a lot of redundant information that we can remove from the neural network without affecting much the accuracy. Okay, so basically by reducing the model, we can have 80% smaller models that are much faster, consume less energy, with a minimum impact in the accuracy. And just to finish, and just to give you a real world example of what does it mean for a customer. There is this telecom customer that they were developing this internal customer service chatbot. Okay, basically they have around 8,000 sales representatives in different places of the world, and they have these shops where you can go and ask for information about your internet connectivity or whatever, and these sales reps basically attend you. Those sales reps needs to manage more than 8,000 documents. Basically, this chatbot, what it does is goes through all those documents and produces an answer to a given question, right? And with applying, they were using Llama 3.1 8B. And what we did is to produce a compressed version that would reduce 80% reduction in memory, 60% in the number of parameters. And just by using this compressed model, the cost was half. So we could produce basically the same value with half of the money again. And the costs are high. The costs are high for that particular use case. We reduce 70%, 78% the storage requirement, since we need to keep less copies of this model, and reducing the cost. In this case, they own the data center, so the models run on their infrastructure. The models does not run on the cloud. So energy, it's important also for them to save energy. In that case, it's the compression that we applied to this model, we didn't lose any accuracy against the customer benchmark. Okay, here we didn't lose any accuracy, and also the inference speed up is much faster. So we have 46% faster time to first token. Okay, and that's it. And that's what I wanted to explain. Thank you very much, guys.
Thank you very much. Again, a new approach to deal with the AI infrastructure, how to optimize, and a really amazing work. I have a question for you regarding the timeline of adoption of such quantum-inspired, comparing to what is like used today, how to make this attractive. For example, you are showing very interesting accuracy, very interesting optimization. How to attract the adoption of such kind of solution, especially you have a sales background.
Mm-hmm. That's a good question. So adoption in this case, it's kind of easy because you don't fundamentally need to change the hardware that it's running this model. You don't need to change the software layer that's running these models. The original model and the compressed model are compatible. So wherever you run the original model, you can run the compressed model. Okay, so the adoption is easy. And to make it even more easier, we have recently deployed our models in an API infrastructure on Amazon Web Services. So it's really easy for the customers to test. There are many customers that are at the POC stage, and they want to experiment with the technology. For those cases, the API is convenient because instead of pointing to ChatGPT or Gemini, you point to our API and you can experience those benefits, especially if you're using the API, what you experience is cost reduction. So it's really easy to move from ChatGPT to our API. And then if you are convinced about the technology, about the cost, then you can use those models internally. So whatever you were running the original model, you can run the compressed model. Okay, so what we try here is to remove as much friction from this onboarding process, from onboarding a customer process as possible.
Mm-hmm. Perfect. Thank you very much again, Victor. So I would like to invite Cedric Hola to to the floor. So Cedric is the program manager for the Sustainable Semiconductor Technologies and Systems program at IMEC. So he has a long experience on the topic at IMEC and University of Michigan. So today he will talk about the environmental impact of AI infrastructure. So Cedric, the floor is yours. Please go ahead.
Thank you very much. Can you hear me and see my slides?
Perfectly.
Okay, very good. Indeed, so I'm here from the company IMEC. I just wanted to say a word about IMEC before getting started. IMEC is a big R&D center in the field of micro and nano electronics that has been pioneering the semiconductor roadmap. And so my background is not AI. It is really about chip manufacturing, but there is no AI that is running without chips. So it is also an interesting viewpoint. And so in IMEC, it has grown over the last, I would say, 30 years to become a quite big research center. There are more than 6,000 employees from all over the world. We have world-class infrastructure, and we are actually pretty much talking to every company that is active in the field of semiconductor manufacturing. And this is actually a sky view of the campus that we have in Leuven that is very close to Brussels. Where there is a very advanced R&D infrastructure. So we are not doing chip production in IMEC, we are really doing R&D, but we have a fab that is, actually we have 3 fabs that are equipped with, let's say, industry relevant tools, and we are doing a process validation and tool validation for the industry. And recently also in the frame of the EU Chip Act, there is a important investment into a 4th fab that will be located here on the picture, and the construction is actually going to start very soon. And so my activity within IMEC, I am the program manager for a program that is called SSTS. It's a Sustainable Semiconductor Technologies and Systems. The program is 4 years old, and we have a number of, we have 26 partner companies who are co-funding the program. And the core mission of the program is to help the integrated circuit manufacturing value chain to reach its environmental sustainability targets. And I would say we have 2 main activities within the program. The first one would be on the assessment. It is really the quantification of the environmental footprint, for example, the carbon footprint of making a chip. So we are modeling in order to calculate carbon footprints. And then we have the improve strand that is about doing R&D to address hotspots. For example, a reduction of greenhouse gas emission from certain process steps in the fab. And so with this, I'm just moving to AI. As I said, I am not an AI guy. I'm really, from the chip manufacturing. However, there's a huge connection between the big AI expansion today and the semiconductor manufacturing. And actually that connection is really fueled by the fact that today, especially with the emergence of those large language models, there is a rapid expansion. It's actually an exponential expansion of the chip needs. And essentially, it's very well shown in this plot, is that if you want to increase the AI model accuracy and also its complexity by going down on that graph, that is actually to lower the test loss here, you need an exponential increase. And look, and those are only log scales, an exponential increase of computing, of dataset size, and also of parameters. And those 3 have to come hand in hand. And from my eyes as a semiconductor manufacturer, this is more memory, you need more computation, you need higher performance. Everything is actually exponentially scaling, so you need more chips, and you need also more complex chips. And that is really rising quite fast. So we are in let's say, such a trend today that is just accelerating with time. And essentially, with an exponential trend, we may wonder where's the limits. We talk very often about the power wall, the fact that at some point AI is, if it continues the rate it is, within a few years, it's going to consume more power than is available on this planet. But maybe before we reach the power wall, there will be a production wall. That is actually the chip need will be so gigantic that the semiconductor industry is just not able to follow. And there are other walls here. And by the way, we are just showing them there, but this is a very qualitative plot. We don't know what is going to where we are going to reach first. But here, and that is coming from SST's program, the sustainability wall, we also wanted to map it there. So how to address the sustainability wall, given this exponential increase in AI data center and exponential investment? It seems important in our eyes to have an early phase sustainability analysis to really understand what is going to be the impact of those massive investments that are going on. And so we needed for that to have standard reliable methods to report the carbon footprint, but also strategies to minimize AI environmental impact. And that is not only about the decrease of energy, higher energy efficiency, as I will show. And so in order to try to do a quantification of the environmental footprint, we are using a method coming from environmental science that is called life cycle assessment. And here's a small definition of what we're doing. The model that we are developing, we have called it Energon. And it's actually the combination of two models. There is one model on the embodied footprint, and the embodied footprint would be the footprint of making all the chips and all the infrastructure that is necessary to deploy a data center. And so for that, you need a system configuration. You need to fabricate all your chips in a certain fab. Those are different components. You need logic, memory, storage. You need interposer for chiplets. You need then to cut your wafers into dies. You need to package them. And all of that has a footprint. And one aspect, by the way, that we are not taking into account in the scope of the present study, it is, I would say, all the non-silicon stuff. That could be, for example, the PCBs, the fans, the chassis, but beyond that, the infrastructure. But then if we also want to look at the operational emission, this is about the energy consumption of a data center, for example. We are developing the model that is called KLIS. It is based both on the system configuration, but there also on a certain job that has to be executed, for example, large language model training or inference. And so there, again, we are making a number of assumptions in order to develop realistic system configuration, but also realistic job to be run on the data center. And the case study that I just want to show today, it's about deployment of such a NVIDIA A100 DGX SuperPod. So one node is going to look like that. It's actually one node is really full of very advanced chips. And probably the most advanced ones are going to be the GPUs, but there are also a lot of RAM and a lot of 3D NAND SSD. That are embedded within such a system. And so this is just showing the architecture of one such node. This is actually, by the way, a very standard product. NVIDIA has been selling a lot of those as of late. And so if you tear down this node, you are going to find such chips. And as I was saying, probably the most advanced object that is inside are GPUs. But of course, we are in our analysis taking into account a lot of other chips. And then if you take one such node, it's going to belong into a rack, and then the rack is going to be deployed within a data center. And I just wanted to show a picture just to give an idea of the scale of what we're talking about. And so within data center, so each of those nodes, they actually are deployed with those racks. There's also power distribution, and then there will be a lot of other components that are sitting in other racks, but those are not taken into account in the present study. So what is missing for the scope? We don't have the non-silicon part. We don't have infrastructure like building construction. We don't have power distribution units and switching systems and cooling systems. And also within the operational, we are not today taking into account the power distribution energy, switching energy, and cooling energy. The only energy that we are taking into account is the one that is consumed by the chips. So we are making all those simplifications. However, let's say the chip manufacturing is such a energy and resource intensive industry that it is actually the dominant factor in data center deployments. And so now zooming into the embodied emission of a single node, we are using this IMEC.NET Zero model that is based on lifecycle assessment. And essentially, we are developing a model of everything that is happening inside a chip foundry. And just to what we are doing, and that's really the core of my own occupation at IMEC, it is to develop this model. We are collecting data within a semiconductor fab about all the tools, all the processes that are running on the tools, and all the materials that are used in the processes. So for example, electricity consumption to run one process it will be collected. And then we are assembling those process steps within process flows. And so we have process flows for logic technologies like high power computing, system on chip, but we have also memory flow for numerous DRAM and 3D NAND technologies. And we also have a number of models for packaging flows to manufacture things like chiplets. And then on top of that, we are developing a lot of fab models because the combination of those two also requires to have a good understanding of the reality of a semiconductor fab. So we have, for example, the yield models, we have fab timing models, so how fast the wafers are moving in the fab, emission abatement, water model, waste model, etc. But combining all of that together, we are putting together an inventory that is a big spreadsheet to make one wafer, so one 300 millimeter wafer that is full of chips. It takes so much energy, it takes so much of this and that chemical, but there's also so much emission of this greenhouse gas, for example. And once you have the inventory with all the physical flows, you characterize that for environmental footprint. And typically climate footprint, for example, we are going to account for all the greenhouse gas emission directly from the fab. We will take into account the greenhouse gas emission for making the electricity consumed by the fab, and we'll take into account the greenhouse gas emission for the supply chain, that is to make all the chemicals used by the fab. And so with this characterization, we do end up with, for example, one wafer, or for example, for one GPU that is combining multiple chips with advanced packaging, we will compute, for example, e-carbon footprints. And so we have been developing this model for the last 4 years and are, let's say, a recognized player in that field. And so we offer a generic representation of high volume manufacturing fab. And also the model is very powerful because since it's bottom up, we can really deep dive and understand at process level detail what is really the footprint. We can also do projection. We do pathfinding in order to understand what will be the effect of future nodes and future technologies. And then, for example, this is a typical output of our model that would be the carbon footprint of making one 300 millimeter wafer, and that is across multiple technology nodes. So today, A14 is not yet in production, and 2 has just been put in production at TSMC in Taiwan. So this is really the most advanced logic technology out there today. And you can see you have like 1.6 ton CO2 equivalent per wafer to make such a technology. You see that with the complexity, the carbon footprint is increasing. And now if we do this computation for the entire A100 DGX node by NVIDIA, that contains a lot of the highest complexity IC chips out there, this will be the footprint. But what you can see is that what really dominates with head and shoulders the footprint, the embodied footprint of one node, this is going to be the GPU, because that one really contains the most complex chips and also the biggest size with the lowest yield out there. And now moving to operational emissions. So now that we are able to count what is the embodied carbon, we want to count the operational carbon to do one workload. And here, of course, in order to make a study, you need to define what is the job that you want your data center to do. And so here we are using an example of deploying a large language model like a GPT, both for the training and for the inference. And here, for example, for the inference, let's say the team that is developing this model, the KDIS model, is computing all the actions and all the power that is needed in order to run all the action to, for example, perform one inference in ChatGPT. And so we have to do an assumption about the lifetime of the model. So we have to use that model over a certain amount of time. And so what we have assumed here is that there's every time a training period to train the full model. And then we can use it for 1 billion requests. And then we are going to train it again and serve another 1 billion requests until the end of the lifetime of the chips. That has been set to 5 years. So the chips are going, or the nodes are going to stay for 5 years in the system. And so if we do the computation over one life cycle, we see that it's going to last for 86 days before we can move to the next cycles. And there will be about 27.5 days that are used for the training of the model, and then 58 days that are used for the rest. And then we can also compute what is the needed power to operate such a model. So it's about 30, let's say 1/3 training, 2/3 inference with, let's say, with those assumptions. And finally, we can also break it down to understand what part of the node is consuming the most power. And again, here, not surprisingly, the GPU is the dominant chip that is using most of the power of running this model. And now moving to embodied emission. So the embodied emission to run the entire model over the 5 years lifetime, you see that we have this horizontal bar. This is actually the embodied emission. So we are at about 2 kilotons CO2 equivalent in this assumption. And then it really depends where you are running your model. What is actually the carbon footprint of the electricity that you are consuming? If you are in a country with China with a coal-dominated electricity production, the operational emission, the break-even time is going to happen in less than 1 year. So in less than 1 year, your operation is going to consume or emit more carbon than the embodied, and then you are going to emit more carbon. But if you are in a more nuclear energy dominated electricity grid, like we have here in Belgium, it will take actually more than 3 years to reach the break-even time. And this actually plotted under the break-even moment is actually replotted as a function of the data center location, hence the electricity grid that you have available. Of course, this is a pledge to go for decarbonated electricity. And now if we look at running again the model in terms of carbon footprint over the 5 year lifetime for full scope carbon intensity, you see that we have in Belgium, we have a total emission of 4.30 kilotons CO2 equivalent. As a reminder, this is a relatively decarbonated electricity where you see that we have about 40% is embodied carbon emission, and then 60% is about operational. And just as a reminder, 1 kiloton CO2 equivalent, that is the emission of about 220 cars in 1 year. This is to run actually the model in a data center that contains 128 nodes. And so making a lot of assumptions, we could also calculate, or let's say offer a number for one conversation with ChatGPT, showing that we are in the range of, let's say, 1 gram or slightly below 1 gram CO2 equivalent. Of course, there's a lot of assumption, and you could see that our scope is not complete. And so this brings me to the conclusion. So we are developing this model in Ergon. This is work in progress. The model is therefore life cycle analysis of AI operation, both embodied and operational emission. And as you could see, as we are running those data center more and more on decarbonated electricity, the importance of embodied carbon emission arises, or the relative importance. And such a model can actually guide AI data center design and technology choice, because we are able to deploy different scenarios and to do a lot of comparative modeling ahead of deployment, also using future technologies. And so we are working at the expansion of the model capabilities. We want to expand the scope, more workloads, more hardware available. So really the idea is to increase the system scale that we can cover with this model, but also the operational scope. And so now I showed at the beginning that AI development today is subject to exponential dynamics. There will be limits. And the climate footprint of running AI is really large. And also the embodied emission is really not something that we should neglect and just think about operational energy consumption. And so the sustainability world requires addressing. So maybe one last question. I will not answer that one, but what is the sustainable usage of AI? We should actually all wonder about that question, because it's, let's say, with the dynamics at scale, we are going to reach that. And with this,
That's great. That's great. Thank you. Thank you, Cedric. Very interesting and insightful talk, and really a big question regarding the sustainable usage of AI. I think it's a wider, let's say, part of the wider definition of responsible AI in terms also of usage and impact. I think we'll have more questions. I mean, time for questions later, but I will invite Evert Japp to the floor to continue to talk about the environmental impact, but also the business perspective on AI infrastructure. So EG is a seasoned entrepreneur. He's an innovation leader and expert in startup ecosystem development. He's, or let's say, he made significant contributions to the European innovation landscape, both as a founder, but also as a strategic advisor. EG, the floor is yours, and please, if you can keep it bit shorter in order to have more time for the panel. Thank you.
Thank you, Heidi. I will be really concise. Okay, so I will try to do it in half of the time that was planned for this presentation. So I'm waiting for Stephanie to put up the presentation because I had issues of showing it.
Okay. I try to share my screen, and please let me know when it's visible.
Yes.
Okay, just a moment.
Okay.
Okay, I'm charging.
Yes, if you can put it in presentation mode, it would be awesome.
Yes.
Okay. So I will start already. I will talk about AI infrastructure and energy issues from a business perspective. So next slide, please, Stephanie. Next slide, please. Hector already mentioned, no, yeah, this is it. Thank you very much. So global data center energy consumption has almost doubled in the last, will double in the upcoming years. It's growing from 3% to 6% by 2030. And Hector even showed amounts that it will go to a totally global energy consumption by 2040. But the thing is that energy is at the moment not a long-term challenge for our society, but it's already on the short-term an issue. When you look at, let's say, the examples we have seen in Ireland, where data centers already consume almost 20% of the national electricity, quite recently there were new bills introduced, new laws, that data centers around Dublin are forbidden because of grid congestion. It's the same issue what we have here in the Netherlands. We have tremendous issues with grid congestion. So you really see the public opinion already turning against the data centers or even hyperscalers. So next slide, please. So that really shows that that's what I believe is that we have truly a big problem with AI as an energy problem. And looking at this, is the first question, of course, that comes to mind is this already a business concern on board level? And it is. So I speak to several boards also in the Netherlands of large multinational with on the stock markets, and everybody is aware of this issue. Why? First of all, it really affects their OPEX. If you're using, let's say, AI infrastructure, or if you're providing this, I mean, every OPEX energy is the biggest part of your OPEX for sure. So you see also that the big techs are really in, mostly the big techs are really in the make versus buy decisions processes, really thinking about having their own data infrastructure, and even moving towards securing, let's say, renewable energy sources. Not only because it's also cheaper most of the times than fossil energy, but also because of reputation and sustainability. As I said before, the risk management, the countries, where do you want to plan your data centers? Where do you want to hyperscale? This is also a very important choice because in the Netherlands, for instance, we have now building projects where people that are completed, where people have the chance to move into their homes, but they cannot because there's no energy available. The grid is completely full. So that really shows that the data centers, they need a new source and a new strategy for dealing with this energy problem. Next slide, please. So you see two core strategic responses to the growing energy demand of AI. So the first one is, next slide, is really trying to do the transition to renewable energy sources. All the large big tech players are now in the play of having long-term power purchase agreements with wind and solar farms, or even with fusion energy. Google, a couple of days ago, they just announced a power purchase agreement with Commonwealth Fusion System for fusion energy of a reactor that still has to be built and is probably not operational before 32 or even 33. They also invest in their own solutions like solar or hydro, or even fusion energy. And of course, and that is what I believe is really an opportunity for some European countries, is they move into what we call green data centers. If you realize that in Norway, 99% of the energy that is created is coming from the abundance of the hydropower, this is a fantastic source to really provide the energy needed to those data centers. And I think also that AI-driven energy management is really something that we have to look at, aligning workloads with the availability of renewable energy. It makes a lot of sense to go that way. So if you go to the next slide, there's a big opportunity, I think, in fusion energy. As I said, Google just announced its procurement agreement with Commonwealth Fusion System, which is one of the leaders in fusion energy in the United States. And I'm also one of the big believers in this technology. Here you see, by the way, a tokamak is where they create where they realize the whole process. I've been at CFS 3 years ago in Boston. I visited them, and they really convinced me that it's not anymore a scientific challenge. The challenge is more in the engineering. And their philosophy is something that I really like, is to say, we design for scale. So everything we do is we build and design technology that can be built with the current tool sets, that can be transported with the current transport methods, and where a fusion reactor doesn't need more than a soccer field to be installed. So for me, the future is for data centers, for those future AI supercomputing data centers, is truly in fusion energy, where they can go completely off the grid and have their own sovereign source to provide them the energy that's so needed. So when you look at the next slide, the other strategies that we see is the reduce of energy consumption. And this is all about efficiency. And this is also a very big opportunity for a lot of European companies to look after new business models and to start new ventures in. And that's also what we see at the European Union. We see a lot of companies coming with solutions, like we see with Hector, which is a completely new approach to architectures like neuromorphic computing that are trying to solve this issue. So we can look in more efficient hardware. We can look in better architectures, where energy is only used when an event occurs. We can start thinking about smarter AI models, and smaller models, more fine-tuned models, and new optimization techniques. But I also believe a lot in efficient infrastructure usage. Edge AI for me is an industry I believe in big time. It was, of course, it started all by the necessity to have, let's say, real-time data processing at the edge of the network, where you can only have almost zero latency. Think in EV vehicles, where you need to process, let's say, data from pedestrians crossing the street real time. But more and more, we also see that edge AI is also a fantastic answer for reducing data transfer to the cloud and creating less overcapacity. So this area of reducing energy consumption is definitely something that opens up new business models for a lot of European startups, and happily to say that we see more and more also at the EIC Accelerator program there. If we look at the next slide, today we already saw a fantastic company in neuromorphic computing, and congrats again to Hector for this. But we also saw in the last batch 2 really exciting companies called Expected IT, Largepool, and Roofline. And I just want to mention them quickly to explain to you what they are. So if the next slide, you look at Expected IT, and with the commercial trademark of Largepool, and what they are doing is they are solving the problem of the fact that off-device data communication between rack servers is really slow. Mostly because we still use an old technology called Ethernet cables to communicate between the rack servers. And they have a solution, a switching solution, as you can see over there on the left, with factory blades that increases the speed of communication between those rack servers by 16 times, which is a tremendous achievement. And this allows, if you have, let's say, 16 independent rack servers, to act as one supercomputer, meaning they can have a shared memory pool. Each CPU can access each GPU in every rack server. And if you look at the next slide, the results of this efficiency is that you can have 10 times more faster computational power. But what I like a lot is the fact that it will reduce energy uses by 50%, and also water cooling. So this is really a solution, a problem that they are solving with a fantastic solution, I believe. Another company, next slide, was Roofline. Roofline, also a German company, and what they are doing is they are having an AI compiler technology that really provides efficient AI inference at the edge. So what they have a deployment platform that allows developers that build AI models to really compile them in a very efficient way, deploy them at every edge device in such a way that it is agnostic, it is retargetable, and it's efficient. And this is important because building AI applications and AI models and training them, should be done in a very efficient way if you want to use this in the edge AI market that is really depending on so many devices with so many new protocols, that this is really important. So conclusion, if I go to the last slide, the opportunity is that energy is a central constraint that we should really take serious, but it's also a competitive lever. It's a big opportunity for a lot of companies to step into this market if they can find the right value proposition that they can validate. And this is exactly where I'm really happy that together with the EIC Accelerator, we are really supporting these kind of companies to bring their technology from tier 6 to tier 9 and to really de-risk these kind of investments. So thank you very much. So Heidi, that was really fast, compromised, concise. I hope it was still a story that you could follow.
Thank you very much. That's great, and really, I mean, that's I think that show that the commitment of Europe in terms of building sustainable and responsible AI is not just talk, but it's in action and in operation, and we are committed to do more. So that's great. Now let's move to the panel, and I'm happy to invite my colleague Samira Nick, who is the program manager for quantum computing, to join me to moderate this session now, and happy to give her the floor to start with the first set of questions.
Thanks a lot, Hedi. Thanks, everyone. Good afternoon. So just a correction, it's quantum technologies, because we are also supporting other types of like quantum sensing and also communication and so on. Thanks a lot for the great presentations, a lot of information to take in. Just to let you know, unfortunately, I have to leave in 15 minutes or so. So then I will hand it back to Hedy. But there was a lot of interesting talks and discussions about energy efficiency. So I would like to address this question to you first. Maybe Shahram, Hector, and Cedric, any of you that would like to talk about what you think about which computing paradigm offer the best energy efficiency for different AI workloads. Maybe we can start with you, Sharon.
Of course, it's very hard to say in a very general way, right? I think that in general, I try to raise the idea or bring the perspective that we need to consider the whole computing continuum, right? So depending on the task at hand, we should be able to select the menu where we would like to, or rather the whole infrastructure should make the selection where to do. But in general, I think the reality is that the more decentralized at the edges of the network you can make the decision in the AI, the better it is, right? So as a general principle, and I think that this means that the whole idea of edge AI needs to become much more prominent as it is. And if I remember correctly, also the European Union was actually planning, I don't know if that happened, to install 10,000 edge servers across Europe. That was also one time, and it goes back to the last presentation also to understand that we cannot just build decentralized big data centers. I think the US might want to do that, and they are of course free to do that. Everything is big and beautiful there, so they should go ahead and do it. But I think from the European perspective, it seems to me more reasonable to shift things more to the edges of the network. That's my take.
Thanks a lot. If I don't know, Cedric, which or
yeah, I just wanted to comment. This is really not my field, so I'm not an AI person, but really more about the let's say from the chip side. However, we do have and I make a lot of activity that is actually aimed at improving the communication within data center, but also in general. And on edge AI, there is research that is going on to actually develop edge AI specific chips, so the chips that would be actually really dedicated to run the AI, let's say directly on boards, even on the consumer goods in that case. So this is also development that is currently happening. But beyond that, I cannot answer on the, let's say, the best operational model to run the.
So what you mean is for a certain application area, you're trying to develop chips for with better efficiency.
Yeah, it would be really, chips that are really dedicated to be able to run on the product itself some degree of AI model. We see a lot of traction, for example, on such a topic in the automotive business, where it would be interesting, of course, to be able to run some of the AI inference on board of the automobile.
Okay, great, thanks. So maybe I will jump to the next question, which is a little bit more to focus on the market readiness. So what do you think about the emerging AI infrastructures that are closest to being widespread, common adopted for commercial adoption?
Let me start here. Yes. So what I really like is 8 years ago, I had a Dutch company presenting this fantastic idea about immersive cooling, which was by that time, 8 years already, a quite wild idea, right? That you have your servers put into a liquid, and that was the way how it was cooled. More and more now, I'm reading about the large big tech players in their data centers are trying to investing in this kind of technology. So for me, this is really a sign that this is one of the technology that is now ready to have breakthrough. Same accounts for me also for Edge AI. I mean, it's already there, but it's really picking up big time right now. And I see that in many more applications and also within a lot of companies that start building. So for me, cooling, liquid and immersive cooling, but also Edge AI is really something that is now really happening.
Thanks a lot. If there is any other complimentary comment on that?
Sure, I'd be happy to also say a few words. Can you hear me?
Yes, yes.
Yeah. So I think in terms of being close to adoption, so I think, for example, the approach that was described by multiverse computing is clearly a software-based approach, like this compression-based techniques that do not require change in infrastructure. So this is likely technologies that, of course, will see close adoption. And then domain-specific accelerators that are built and derived from these type of technologies, because essentially you see the benefits that multiverse computing already gets in existing infrastructure. Now imagine that you can translate that into these domain-specific, extremely sparse type of accelerator infrastructure. So then, with the huge demand that exists today and the huge energetic crisis that we are seeing, as was shown in the last presentation. So there is a very strong incentive for this type of domain-specific accelerators and custom AI chip companies. I think this is very exciting. I mean, we have also shown that there is a demand for this type of infrastructure. So that, yeah, I think it's very exciting.
Thanks a lot. Victor, I don't know if you want to add into this.
I may add something here regarding AI adoption. From my point of view on sales, and I talk to many customers, I see three main barriers to adoption of AI. The first one is costs. Running large LLMs or AI at the scales or even smaller models at the scale is really expensive. So I think this is the first barrier that we need to remove there if we want really to adopt AI. Second one is compliance and security, basically because those models use data that has some confidentiality requirements or data protection requirements. This is the second largest barrier for AI adoption. Bringing AI to the edge might be a solution here, right? If they own the infrastructure, they will feel more safe, or if they are inside the security perimeter. And the third one is training. So we don't have enough skills in the market. So there are many people with the skills, but not with enough training on the technologies. This is a really fast-moving field, and access to people with the know-how, it's a third barrier that we see to adopt the technology. If we can break those three.
I also would like to. So I think that one aspect that got so much attention in the last year or so is these whole LLMs, right? So I think the majority of the people seem to think that AI equals LLMs. And I think that is a bit of a problem now, because it basically focuses the thoughts on centralized systems. And this is very dangerous. I think that many companies would actually benefit a lot from having more result-oriented systems, which are really helpful for their business. And the majority of European companies are SMEs, and they would benefit tremendously for real AI systems which are deployed and not just LLM-based systems.
Okay, thanks a lot. Just one thing that is interesting from all of you talking is, do you think something is missing from from the end users? For instance, are they investing in having experts because I use this expression a lot, being quantum ready, but for AI, do you think that we have this kind of movement or awareness in the final application areas or industries or startups in Europe for receiving all these changes, or you think there is still a need?
It looks like many companies, they are having a hard time finding the right angle and budget to address the problems, right? So, but it's also partially the fault on the AI providers, because they require the companies to have heavy investments, and it takes them too long to actually show some results. So I think the important area is that we need to become faster in showing results which are of benefit to the companies. This is, in my view, very important.
Thanks a lot. That's certainly an important point. So maybe because time is running, I will just ask you one more question before handing it to Hedy. It's about the technical integration. So how do you think that, for instance, neuromorphic chips or quantum computing can work together in future AI infrastructures? I mean, we have multiverse, of course, but I mean, if you can think about further developments and how you think they will play a role in this era.
Yeah, I think, Samira, interoperability is certainly an important component. So we have to make sure that people can use the models and can, for example, leverage the characteristics of novel hardware without losing what they have. I think this interoperability is a key component to make sure that you can transition to other technologies, that you have existing software infrastructure that lets people deploy models without the hassle of programming the low-level details of the hardware. And I think this is a key component for making sure that a new technology is always enabled. I mean, there are also pipelines in place to make sure that you can sparsify models and you can leverage the characteristics of new novel architectures. The more we automate these pipelines, the more we do it in an independent way so that engineers do not have to be involved to convert those pipelines, the easier it is to get adoption on the infrastructure.
Thanks for the good points. Any other opinions?
If I may here, because at the beginning, Professor Shaham mentioned that quantum computers are far in the future, maybe in 20 years' time, and he sees difficult the integration on the quantum computers on HPC infrastructure. I want to say that it's happening already. Quantum computers are going to be integrated in the same that today we run certain programs on CPUs and certain programs on GPUs. In the future, in certain programs, for certain problems or subset of problems, they will be run on QPUs, on quantum processing units. And this integration is already happening. It's a good example, the effort that the European Union is doing on Euro HPC joint undertaking, where they are purchasing quantum computers for different manufacturers in Europe, integrating them on HPC centers. So this is already happening. Of course, with the limitations that the technology brings to the table, right? But this is going to happen, and in the future, for a given problem, some parts of the problems are going to be solved in a quantum computer, some in a GPU, and some in a maybe in a neuromorphic architecture. So that's what I see.
Thank you. Sharma, I don't know if you want to add something to that.
Well, I agree with Victor, of course. I mean, what we have been working on is the splitting the tasks optimally between the quantum processing unit and the classical nodes. We have written a paper, we've done a study on this, it's published on Archive. So I think that this is an interesting area, definitely. I was more referring to the large scale deployment with a special focus on looking how software is written and making the distinction of how software is written in the quantum world and how software is written in the classical world. And there is a huge gap also in thinking. And this is, it requires basically 1 or 2 generations of engineers to actually wrap their head around how to actually combine these two things. This is what I was referring to.
Thank you. It's a great point, actually, because we see it also, I mean, when the startups apply for EIC, for accelerator, it's mainly hardware. And we are lacking this real, you know, a new wave of software developers for quantum, which I think it's a very important point to focus on. I'm really sorry I have to leave, but thank you so much. And I will hand into Hedy to continue the discussion.
Thank you, Samira, and thank you for this interactions. I will go, I mean, I think we are over time, but I have a last question for all speakers, maybe the last words about the competitiveness of Europe. You know, AI infrastructure is a race, is a matter of sovereignty, is strategic. So from your perspective, all of you, what role should EU funding and also regulation play in making Europe competitive in that area?
Well, maybe Hedy, I start here because this is something that is for me. I travel a lot around the United States, also around China. And when I see what's happening over there and I come back to Europe, I'm always getting depressed, to be very honest. I mean, we are not doing enough. That's for one thing for sure. And I'm really happy with all these instruments we have at the EIC, and we're trying to support companies like Hector and Cedric, et cetera, et cetera. But if we really want to, if we take AI infrastructure seriously and we want to be independent and we want to decrease risk here from a geopolitical situation, we should start to invest billions and billions in this industry. And this is possible because what I see happening right now in the Netherlands and probably everywhere in Europe is that now the defense industry, the military industry has suddenly have all this money. So all companies in the Netherlands are suddenly working with the defense industry of finding dual use cases. And then I think it's very important to have, of course, have a very advanced weapon system in place, but we also need to have an advanced AI infrastructure in place that we can control. So I think we should do much more from as a strategic investor, as a European Union, but also be much more Catholic, provide more funds so we can allow, let's say, European companies to really play in a serious role in AI infrastructure. But that's my opinion.
If I might second that, so I think it's as it's just mentioned. So there are mechanisms in place that this is possible to make it happen. I mean, there are initiatives like, for example, the AI gigafactories. There are initiatives in place that just need a little bit more incentive to local infrastructure. If there are not enough incentive on this deployments of infrastructure for local companies, like basically to incentive that, for example, some of the submissions like have a certain level of involvement of local companies. I'm not even talking just about us, but there are other players also in Europe that are also designing infrastructure. If there is an incentive to basically incorporate local infrastructure, that there is a percentage of local infrastructure included into this submission of AI gigafactories or submission of AI factories in general, it definitely helps, right? Because then at least these mechanisms that are in place to create new AI infrastructure also take at least a small percentage of consideration for local infrastructure. Ideally, I mean, if we had the scale to deploy all infrastructure from local companies, it would be great. But just starting with that, at least a small portion to basically incentive companies and new emerging technologies in that direction, so that you see a path of commercialization also starting to, I mean, this is also what the US does. So if you look at the national labs, you look at the supercomputer centers, so they typically have this incentive for local infrastructure companies so that they can like take them to be lifted to a level until they can compete internationally in that field. And I think in incentivizing this for local companies, I think I cannot stress that enough.
I think that Europe has the opportunity and the challenge at the same time to create an infrastructure which is a reflection of who we are. What I mean is the decentralized and distributed support for everything that we do in Europe. And this is something that I'm a bit negative on this, unfortunately. I don't think that our leadership in the European Union has the guts to actually implement that. And that goes back to this whole idea that all the money now is being siphoned into weapons. And I believe that the infrastructure for the benefit of the whole society would be much better spent if we focus on the infrastructure AI infrastructure for everybody, and the SMEs in particular. This chance, we will miss this chance. And this is a very important opportunity that we would have. But I don't think that Europe is going to act on it in an appropriate way, in a timely way. And this makes me worry, I think.
If I may add something here, I think I am very optimistic when I look at Europe. I think we have excellent researchers, we have excellent entrepreneurs. They are ambitious. They are not risk averse. That many people love to say that Europeans are risk averse. What I think it's missing is a single capital market union. So when you go to the stage, you can raise. You have 3 million revenue, and you can raise 1 billion in the stock market, right? And this is what we lack in Europe, really access to capital, so that technologies like the one developed by Hector can scale in size. And this is I think one of the huge biggest problems that Europe need to fix ASAP if we really want to play something in AI. And the second, I think it's regulation. I think we have too much regulation, too many regulations that we need to simplify. And right now, even if we are, when you try to commercialize something in Europe, you really are talking about 27 different markets. When there's free movement of people and goods, if you want to sell something in Germany, it's different to sell something in France, and you need to comply with different regulations. So I think this is super complicated especially for any startup. Okay, so scaling in Europe is much more difficult because you lack the money, and basically if you want to look for customers, you need to look for 27 types of different customers and regulations. And I think that's a challenge.
Maybe if I may add another very short point. Another thing, since there are all these particular characteristics in the local ecosystem that were already highlighted, one thing that could be beneficial here is to strengthen cooperation between the individual companies, like for example, between software-based companies, between energy production-based initiatives, between infrastructure providers, so that there is more unity, because essentially in the US, you can have the luxury of have fragmentation on the different companies, because you, as was mentioned by Victor, you can have access to capital, even though if there are many companies centralized within the same domain. I mean, just to mention, Silicon Valley already has three of the biggest startup in terms of infrastructure, Cerebra, Sambanova, Krok, they're all sitting in the same place, and they all have big access to capital. So then you at European level, it could be beneficial to promote and incentive this cross collaboration between different units. So that's not the individual infrastructure providers are not such, there's not such high fragmentation, so that then at least the capital can be leveraged better. And this type of research goals at scale, I mean, we saw this initiative from there that basically unified different companies within the RIS5 domain. These type of infrastructure providers are extremely interested because they put together different consortiums, different companies, and it helps to unify, like basically infrastructure providers. I think more like this definitely is particularly beneficial for an ecosystem like the European ecosystem.
That's great. Cedric?
Yeah, I just wanted to say a word on from chip industry side. AI does not exist without chips. And chips will stay a global business, in the sense that the supply chain for making a chip is so highly complex and distributed across the world that Europe would not be able to develop its chip industry on its own. Maybe just to give an example, the most advanced logic chips are coming from Taiwan today, TSMC, but TSMC cannot function without ASML that's based in Netherlands. And of course, I mean, the same logic applies across the entire supply chain, where everybody is dependent upon everybody. We are dealing with an extremely complex industry. And so with the recent EU Chip Act, there has been quite a lot of money invested to both actually develop new foundries in Europe, but also to help where Europe already has its strength, and actually to reinforce its position within the supply chain of chips. Of course, the chip industry in Europe has been historically more oriented to automotive chips. Those are older generation, whereas AI actually needs the most advanced stuff, which is actually something that is very difficult to produce at yield. So in a sense, I would say from a chip side, it is not impossible to function just in isolation, and it is not possible that Europe would become just a sole player to produce its own chips entirely, and so there the position is more about reinforcing the strength that we already have, and there I would say the EU Chip Act is acting. I would also say, yeah, maybe a word, and that's more from the sustainability point of view. Our industry is at risk. There's risk actually not only with climate change. I mentioned that a lot. The water question is really an important one for foundries, but I believe also for AI data center, we have to address such questions. And finally, on resources, we are not running any industry without access to resource. And today there's a, given the geopolitical tension, but also the scarcity of some resource, and we have to mine deeper and deeper, even underwater today. We are also facing risk that we need to be addressed. And so there's not unlimited deployment of energy, and there is not unlimited deployment of industry and infrastructure that is possible in today's world. So we have to be aware of those questions.
Perfect. Thank you very much again for all the speakers. Very insightful webinar. I learned a lot of things. I hope it's the same for our attendees. This input will be used for preparing the roadmap innovation on AI that we're working on to be ready for the end of the year. So we'll back to you to get more insight, and the recording will be also published on the DeepSync website soon also. So we'll share this with you and all the attendees. So thank you very much again, and hope to see you again in the next webinars. Thank you.
Thank you very much. Bye-bye.
Thank you very much,
Thank
guys.
you. Bye.
Bye.
Thank you. Goodbye.
Thank you. Bye.
Thank you. Bye. Have a good afternoon.